morning. Here we are once again. It's the physics video lecture. Physics 105A, video lecture 3. So what are we talking about today? We just finished with a discussion of vectors, pretty much just formalities. We're going to continue on with that, not formalities, formalism. We're going to continue with that, and we had just done vector algebra. I'll briefly mention something about differentiation, and then we'll go into kinematics. So to begin with, differentiation of vectors, something we need. So suppose we want to take the derivative, say we have a vector A as a function of a parameter u, okay? And we want to take its derivative we can express that in a couple of different ways. When we do the kinematics, I'm actually going to do the constructions with arrows, but right now, suppose we have the vector in terms of it being an ordered triple. Okay. Then we can call that dAx with respect to the parameter, which is often going to be the time, but right now we just have some parameter d sub ay, d sub az du. So yeah, this, you can see that the compact notation is already nice because this here is actually 3 derivatives. We could also have, maybe I'll just continue this. Or how about, yeah, we'll just continue this. Or we could say it's the derivative of the vector ax I hat plus ay j hat plus az k hat. So that's the vector expanded in terms of its orthogonal unit vectors. And then that would be dAx du times I hat, and the same for the other two components, y times j hat dA du z times k hat. So yeah, there are different ways of writing vectors. And you'll notice these unit vectors are not, they're constant, they're not dependent on any parameter. So that's why we just have a simple differentiation like that. Good. The same thing can be done with integration if we have a vector depending on a parameter. So that was differentiation. And I'll then mention integration. So again, we have a of u, vector as a function of some parameter, and then the integral of a of u du is then those 3 integrals. And we had a homework problem like this, of course, with the constant acceleration problem. So that's what I assumed you guys would probably figure out. But yeah, a of u du would be any one of these ways of doing that. Let's just go ahead and write one of them down. We could say it would be integral ax of u du I hat plus ay u j hat plus kz u k hat. Good, so differentiation and integration of vectors. Now what I want to do is talk about kinematics, and we'll call this kinematics of a point particle. It just means it's an object whose dimensions are small with respect to the trajectory that it's tracing out. And so here's this little red cap. If I were to throw it across the room, we could just say, okay, that's a point. It's got a location. Got to remember to bring tennis ball to class. That's always good to throw around. So kinematics of a point particle, and we're talking about one point in space, motion of a point, and these kinematical concepts are foundation of what we're doing. We already wrote down net force equals mass times acceleration, so we know where we're headed. We have to talk about position, etc. So kinematics of a point particle, we have position, and we're just going to call it R for now. And R is a vector. Now here's my origin. This is the vector R, and that point at the tip, that's what we're tracing out, or what we're tracking. So we've got position R, and because, say I were to launch tennis ball I was just mentioning, and it'll fly across the room in a trajectory. Then we can see that R actually changes in time as it tracks out this object. And so R is a function of t, and we've already talked about our vectors, so we know it's got 3 components, okay? But now we want to do calculus. We want to actually do these derivatives. And I'm going to start with just an analysis of these arrows here. So we've got position R of t, and then we have, let's just start numbering. We've got the position, then we've got the displacement. And the displacement we will call delta R, and it's R, well, it's a difference, so R sub, I'm just going to call them 2 minus R sub 1 for the moment, okay? It's a displacement, difference of 2 vectors. And with my picture right here, I'm just going to keep going. So if this was that first point, and this is the second point, so I could call one of these R sub 1, one of these R sub 2. It's the second one minus the first one. And let me around with these here. Let's go ahead and put our, so we had that position right there and right there. Okay, those are those 2 points along this trajectory. We can even dot the trajectory. There we go. So there's our displacement, and vectors add like arrows. And so this displacement vector points from the initial one to the final one. So that is our delta R. So I'll put a note for you here. If you just add these arrows, you would say I've got R1 plus delta R is equal to R2. So R1 plus R2 minus R1 equals R2. Right? So that delta R there, you see trivially, this is just an equality. So this is something you always want to is our delta R. Be aware of. So that displacement vector, good, I'm going to leave that. Keep this picture up here. Just point at it. What we're going to see is that displacement vector is essentially tangent to this trajectory that I've drawn. And we'll see why in a moment, or what the significance of that is. So in this line of concepts, you got position, displacement, and the next one, 3, is velocity. And the velocity, the letter V with a vector, it is the limit as delta t goes to 0 of r of t plus delta t minus r of t, these are vectors, divided by delta t. So clearly that's the derivative, that's the first derivative of a vector, okay? So that would be, that's my delta r. So actually I should just as well have written limit delta t goes to 0, delta r over delta t, same thing, and that is the derivative, dr dt. Okay, so we want to look at that geometrically for a moment. Yeah, if I were writing this down again, I would actually define it as this, and then that, and then that. But that doesn't matter. We want to look at this geometrically. So we've got that delta r up here, and as we let delta t be smaller and smaller, this becomes shorter and shorter, and more perfectly tangent to the curve. I'll even redraw that because it's so important. In fact, let's make this a big picture, and we'll work on this. So we've got this trajectory. We've all seen a trajectory before, maybe a little better. Once again, okay, we've got, this is the arc, or tennis ball flying up and then back down again. And these are these vectors. Okay. And these position vectors are now interesting. We see that on these displacements, essentially the velocity vector is exactly tangent to the curve in that limit, but even these displacements do a good job of showing what's going on. Okay. So we got the velocity in terms of the arrows. That's the point I'm making. Now this next one's even better. Let's even have one right here as well. Because what you'll notice now, since we're talking about a projectile that we've worked with before, is that the velocity vectors, we'll call these velocity vectors here, are themselves changing. Okay. So velocity is the change of the displacement with respect to time. The acceleration A is equal to, and I'm just going to use the construction I had here above, delta V over delta T, right? The delta V is defined analogously to the delta R. And we have some on the board right there. So it's the limit delta V over delta T equals dV dt, derivative, and since this is a second derivative, it's also d squared r dt squared. That's our acceleration. We have that there in Newton's law. Now let's look at the construction here for our projectile. I'll just write projectile, something you can all identify with, okay? And you'll notice that we have V pointing up and then V pointing down, okay? So I'll take these two outside ones. So the delta V, so for our example, which is this right here, here's our delta V. It is the V final minus the V initial. Okay. On the V initial, here we're drawing arrows, okay? The V initial is pointing uphill, the V final is pointing down a bit. And what is this difference vector? That is the same as going from here plus a negative, so the difference of these two vectors, and I'm going to draw it in red. This is the punchline of this little discussion. The difference of these two vectors making up my delta V is pointing straight down. My example was a projectile. This acceleration is nothing other than the acceleration due to gravity. We know it points straight down. So the fact that you get an arc here for your projectile motion is geometrically necessary when you have, acceleration pointing straight down. Okay, so we have position, displacement, velocity, acceleration applied to your basic projectile motion through a tennis ball or something, and done just at the level of arrows. That's important now, because you think, well, we're just doing everything analytically, and it's true, but we're driving home the point that these vectors, by displaying them as arrows, we're driving home the point that they're independent of the coordinate system, right? Whatever coordinate system you choose, it's still going to be that particular arrow. That's the idea, to be that particular vector expressed in many ways. Now, of course, we start with Cartesian coordinates, but we soon move on to other coordinate systems, and we'll see some stuff we haven't seen before. Okay, let me put some words here just as a note. Acceleration directed down. This is G, right? This is the gravitational acceleration along with its direction when we're talking about a projectile. Okay, good. So that homework assignment we had was the integration of the constant G, okay, namely the vector that was pointing down. So on that homework assignment, I'll just make a little note of that. Well, actually, the homework assignment was more general. It was just a constant acceleration. But if we take that as G, it would have been pointing straight down. So I'll just put a little note for what I had as the homework assignment. So note on our homework, we had integrate d squared r dt squared equals a, which is constant. The projectile motion case that you guys certainly have seen before is A equals G, and then usually what we do is, put it in we could have I hat and J hat, for instance, X and Y axes. In that case, we'd say A equals G equals minus G, which is our 9.8 meters per second squared, and then J hat. That would be how they express it in terms of the vector. So this problem is really going to be the same as this one, with A pointing in any direction. Okay. And here for gravity pointing down. Okay, good. So we have that. I mentioned other coordinate systems, and I think that's what we're going to start with, yes. Before that, though, I see, yeah, let's add this to here. I could have actually said these things up there. So we have, right, the position, the velocity, acceleration. I do have to say something about magnitudes before we leave this. So in particular, let's say, magnitude of the velocity. This is something we're going to need a lot. So once again, we have this v equals dr dt as a vector, that's fine. The magnitude of v just use absolute value signs. That's the magnitude of that particular vector. And depending on your coordinate system, we can start this way. Vx squared plus vy squared plus vz squared. Okay. So that would be the magnitude of that vector. Sum of the squares, Pythagorean sum. But there's another way to express it that's also very useful. We can also say it's the square root of v dotted into itself. Okay. So the dot product of v, you'll recognize it's the sum of those components squared. Okay. So we can do that there. And here's some nomenclature I do like to use sometimes. Suppose I want to write v squared then apparently it's just the dot product of the vector with itself. That's the square of the vector. So I can use this and this at the same time means, actually let's continue this one here. That's v without the arrow on top, v squared. Okay. So this is just useful nomenclature. If we're going to write v squared, this is what we need. And if we write v squared without the arrow, we actually need the same thing. Good. So this magnitude of the velocity, you can do that with other vectors as well. It comes up off with velocity. Okay, I'm going to check the time and move on into an interesting topic. Good. Okay. Okay, what we're going to do next is this whole formalism in plane polar coordinates, and then I may give it to you to do in spherical polar coordinates. But first I have another comment or another definition about nomenclature. In physics, we use dots for derivatives. So, here we go. Let me just draw this first. Here's a definition. R vector dot refers to this time derivative here. This is so common in mechanics. We're gonna be doing a lot of it. We can actually mix it up. We just have to be comfortable with both of these. And our second derivative is then d squared r dt squared. So when you're doing a complete time derivative, as opposed to a partial time derivative, complete time derivative, you often just use the dots here. It's it's just a compact notation. Okay. So example, suppose I have f of let's save that one. Let's save that one. Let me continue this thing here. Also, r dot would be dr dt. Here I wouldn't be talking about the vector. Here I would be talking about the magnitude. Or d dt of r. But what is this r here? I'm talking about the magnitude x squared plus y squared plus z squared. So now we would have to have some chain rule involved. This would be a pretty compact expression here, but what do we have to do to take this derivative? Here we have a chain rule, and it's actually going to be a pretty complicated object, even though we're just calling it r dot, time derivative. So, we tackle this. We have, let's just put a period there. Here we're looking at what I was about to write down before. So, d dt f of r of t that's actually going to be a gradient f of r, and then that's going to be dotted into r dot. So here we need the chain rule. We're working on this thing, and you know, I think I will put this as a homework problem because everything's been set up now. Your f of r of t would be, your f of r would be the square root, right? And then the r of t is that the x, y, and z are implicitly functions of time. So yeah, let's go ahead and do this as homework. And I'll set this up for you guys. I'll set this up. So what do we have here for the gradient of what is gradient of r equals gradient of square root of x squared plus y squared plus z squared. Okay. Question mark. We'll just do one of these. dr dx. Remember, the gradient is dr dx, dr dy, dr dz. It's a vector. Those three components. It's going to be 1/2 root x squared plus y squared plus z squared. And then we've got the chain rule. We've got 2x. 2's cancel. X, and this denominator is r itself. So the dr dx is x over r. The gradient of r is therefore, squeezing it in the bottom corner, don't lose it. So the gradient of r is equal to the vector r divided by its magnitude. So the gradient of this expression here is actually a unit vector pointing in the same direction as r. Good, very important example. And from here, and this understanding, you can get to here, okay, to this expression here. And I'll just write here chain rule, multivariable chain rule. Multivariable chain rule. Okay, this is something we're going to see a lot of, but it fits in really nicely right here. And so, yeah, back to what these definitions are. We use the dot just for the time derivative, And we're going to be seeing a lot of that. Okay, so now I better consult the clock again. Perfect. Good. So now we want to tackle the plane polar coordinates and all of their derivatives. In Cartesian coordinates, we feel pretty confident we have position, displacement, velocity, acceleration. Okay, nothing fancy. Plane polar coordinates is going to get interesting. Okay, plane polar coordinates. Most of you have seen these before. I will just remind us, we start, say, with x and y Cartesian coordinates. So we have any old vector. And this point here, we're now going to express in terms of the length of that vector and the angle that it makes with the x-axis. So now we've got the vector r such that our x is equal to r cos phi, y is equal to r times the sine of phi. But what we want to do is express all of our kinematic quantities in terms of r and phi and not in terms of x and y. And so, bracket here. So those are the coordinates, so yeah, we have an r and a phi instead of an x and a y. And of course we can invert these things as well. So let's start expressing what is r. So here, r is of course equal to the square root of x squared plus y squared. And you could say phi is equal to the inverse tangent of y over x, first quadrant. We don't actually usually have to do this, but we have it here for the record. So, since there's that, we can also write it this way. R is equal to r cos phi, r sin phi. It's our ordered pair. And what we're going to do is pull out r cos phi and sin phi. And this vector here, which has the same direction as r itself, right, is a unit vector, and we give it a name. Now, let r hat equal cos phi sin phi. R hat is equal to cos phi sin phi and is a unit vector. So r hat magnitude is equal to 1. So to work with plane polar coordinates, we're now going to do the following. We have, and this is important, I'll put a box around it. We now have r is equal to r hat. Put a red box around there. And this is the object we're going to continue working with. So r is the magnitude times the direction. This is a unit vector, r hat is. It's no longer a constant unit vector like ij and k were. Okay? It's a unit vector that moves with the point that we're tracing, that we're investigating. And at the outset, that seems like it's a bad thing, but we'll see, it's pretty interesting. So now we're going to do the kinematics with this vector right here. It's thoroughly introduced. And we're going to find the velocity and the acceleration. So that's position. I'll write it down again. So we have position R equals R hat. And I'm going to be able to make use of a picture. I'll draw another picture in a moment. So what comes after position? Of course, velocity. Velocity V, I've already introduced that dot expression, so I'm just going to say that's R dot for short. Okay, it's a time derivative. And now we're going to apply it up to here, so we have R dot R hat plus R hat dot. Well, we think we know what this is, okay, but what is this? So what is R hat dot? What is R hat dot equal to? Well, just for the sake of old times, ddt of R hat is the time derivative of cosine phi sine phi. But now phi is a function of time, right? Because this thing could be moving around. So that will be minus sine phi times phi dot, right? We've got the chain rule here. Phi is a function of time. And then this derivative of sine is cosine of phi, and that too has chain rule phi dot. So we can pull out the phi dot, and now we have minus sine phi cos phi. And interestingly, this is clearly also a unit vector, right? Sine squared plus cosine squared is 1. This is a unit vector, and we're going to give it a name, phi hat. So that is equal to phi dot phi hat. So just to hold on to this, we have R hat dot is equal to phi dot phi hat. Phi hat is equal to minus sine phi cos phi. And I'm going to collect this result right here, and then I'll draw a picture. So this object, we now see that V is equal to R dot R hat plus R phi dot phi hat. See, R phi dot phi hat. So it's equal to R dot R hat plus R phi dot times phi hat. So these are unit vectors that move along with the particle. And not as complicated as it looks. What about V squared? Let's put a box around here, because this is, of course, eventually we'll gather all these things into one nice list. So there's our velocity in terms of these unit vectors. And now let's do V squared. Next, V squared is equal to V dotted with V dotted with itself. And I'm going to send this up and do this on another board. good. So continuing. V squared equals V dot product with itself. We're going to write this one out. So R dot R hat R phi dot phi hat. Do the dot product at R phi dot phi hat. Okay. So this gets interesting because we're just going to have four products here, and we're going to write them all out. So R dot squared R hat dotted into itself plus this outside and this inside are going to be the same. So we'll have plus 2 R phi dot not so fast. So we've got first for the outside we'll have plus and the inside will be the same. 2 R dot phi dot R hat dot phi hat, and then the last one will be R squared phi dot squared phi hat dot phi hat. Okay, so we're taking this step by step, but you'll notice these are unit vectors. So this is just R dot squared, and R hat and phi hat are orthogonal. Okay, so that's going to be plus a 0, and then phi hat is a unit vector with itself is equal to 1, so plus R squared phi dot squared. Because, and I'll just put this here, because R hat dotted into phi hat is equal to, they're both up here now, are they? Yeah. If you dot this into this here, dot product of these two, cosine times minus sine plus sine times cosine. So that's 0, equal to 0. So we actually have a really interesting result. We have v squared in plane polar coordinates, r dot squared plus r squared v dot squared. Now I'm going to get the acceleration started after I check the time. Yeah, that's perfect timing. So next acceleration actually before we do the acceleration, let's first look at this picture. So we're x and y, we had a point here, r, right? So r hat was in the same direction as r. So I could draw r hat like that. This was r. And phi hat, which is this right up here, minus sine phi cos phi, that is this vector. It's a unit vector. It's orthogonal to r hat like that. And this will all make perfect sense if you imagine a circular motion. We'll talk about this in terms of uniform circular motion later, and then you can see that as you go along a circle, r hat and phi hat just retain their orthogonality even though they're moving around. Yeah, so we've got v squared in terms of the acceleration. We're going to have a is equal to v dot, and I'll write it as a time derivative because it's an operation we still have to do. R dot r hat plus r v dot phi hat. Okay. So when you do we're going to leave it right here. So we'll pick this up next time. You guys may want to work ahead though. When you do these time derivatives, you can see you can have r double dot r hat plus r dot r hat dot. And then here you're going to have to be a little more careful with the chain rule. You already know what r hat dot is, but you're going to have to discover what phi hat dot is. And then you do this entire chain rule, and you substitute these R hat, etc., phi hat, and what we're going to get is something, so this is after we do all the work, we're going to get something that's proportional to R hat plus something else that's proportional to phi hat. Okay, good place for us to stop. I did have one chain rule homework here problem that will probably come up next week. I'm going to go over that and figure out exactly when that's due. Actually, definitely due next week. Good, so let's leave it at that, and we'll pick up next time where we left off. See you guys next time.